Next session, we are going to solve the most important, most repeated inorganic questions. Let's get started with this question. Total number of molecules or species from the following which will be paramagnetic is. So you know oxygen is paramagnetic, right? 16 electrons, so paramagnetic. And O2 plus, 1 electron less, 15 electron. Again, that is also paramagnetic. O2 minus, which is 1 electron more, still that is having 1 unpaired electrons. So which is again a paramagnetic. And talking about NO, that is having an odd electron. So that is also paramagnetic, odd electron. So which makes again a paramagnetic. And then CO, it's not paramagnetic, all are paired there. Then K2Cl, NiCl4, where Ni which is in +2 oxidation state, nickel 2 plus. Nickel 2 plus is 3D8. This is a weak field ligand, so which will not undergo pairing. So this is also paramagnetic. And talking about this cobalt complex, amine, it undergoes pair up, so it is not a paramagnetic species. And nickel cyanide, strong field ligand, so not a paramagnetic species. So 1, 2, 3, 4, 5, 6. 6 is your answer. The spin-only magnetic moment value of N plus ion formed among nickel, zinc, MnCu that has a least enthalpy of atomization. Here N is equal to the number of diamagnetic complex among this. Okay, they have given many words over here, but the question is very simple. They are asking the spin-only magnetic moment value. That we will do it for paramagnetic compounds, right, which are having unpaired electrons. But what they have said is N belongs to diamagnetic complex that is having least enthalpy of atomization. So among these four, nickel, zinc, manganese and copper, zinc is having least enthalpy of atomization. So which makes, what is the number of diamagnetic complex present over here is 2, zinc and copper. So which will have diamagnetic, no unpaired electrons. So which makes the spin-only magnetic moment as 0. That doesn't have any electrons in it. Next question, bit lengthy but doable. Number of paramagnetic metal complex species among this. Again, with the same number of unpaired electrons. Paramagnetic, but that also same number of unpaired electrons must be there. So let's do it. Here I have cobalt 3 plus, which is cobalt is 3d7, 4s2, 3 plus is 3d6, which makes T2G6 for octahedral. That is not paramagnetic. And talking about the next one, oxalate, that is a strong field ligand. So cobalt 3 plus again, which is T2G6 EZ0, and manganese Cl6, which is manganese 3 plus, where that will have T2G3 because Cl is in weak field ligand, Eg1, that is paramagnetic, and manganese with Cn, that is 3d4, T2G4, Eg0, that's again in paramagnetic. Cobalt F6, that is also T2G4, Eg2, and iron Cn complex, which is in T2G5 Eg0. Anything left? Yeah, F6 3 minus, which is in T2G3 Eg2, right? Because fluorine is in weak field ligand. So among this, which are all paramagnetic? So many compounds are in paramagnetic, but which are all having the same number of unpaired electrons. MnCl6 3 minus. So unpaired electrons are 4. And cobalt F6. Here also the unpaired electrons are 4. 2 from T2G and 1 from Eg. So answer is 2. The complex that shows facial and meridional isomerism. In our crash course of coordination complexes, we already explained what are the isomerism, which complex, which type of complex that can exhibit. If you didn't watch it, please do check it out. A3B3 complex which exhibits facial and meridional isomerism. This is a very important because this is something unique, no? Apart from cis and trans DNL. So A3B3 type, that is option B. 1 mole of octahedral complex of the compound, cobalt is there, 5 amine, 3 chloro is there. It gives 3 moles of ions and dissolution in water. 3 ions it is formed. 1 mole of the same complex reacts with excess silver nitrate to form 2 moles of AgCl. So what is the structure of the complex? Simple question. Very simple question. 3 moles it will form. So apart from the complex, it is having 2 ions in it outside. Right? And second clue is with Ag and O3 it forms AgCl, 2 AgCl, which means those two, that is Cl. Remaining, what do I have? CO, NH3, 5 and 1 Cl. Very simple. The number of unpaired electrons responsible for the paramagnetic nature of the following complex species. So here I have Fe3 plus, cyanide is there. So if you fill this one, T2G and Fe3 plus is 3d5. So 1 unpaired electron, and Fe Eg is empty, F6 3 minus, but this is in weak field ligand, so which will go up, and COF6 CO which is in 3 plus oxidation state, 3d7 3d6 it will become. So 1 2 3 4 5 6. Then MnCN6, Mn that is in plus 3, 1 2 3 Cn, no? So 3. The number of unpaired electrons responsible for paramagnetic nature. Here I have 1 and 5, 4 and 2. That is the answer to this question. The homoleptic and octahedral complex of cobalt 2 plus and H2O has dashed unpaired electrons in the T2G set orbitals. They mentioned that is octahedral, ligand is H2O. So what is the complex? Cobalt, H2O 6 times. That doesn't matter. I have cobalt 2 plus. Cobalt 2 plus is 3d7 configuration, right? So water is in weak field ligand. So T2G set 1, 2, 3, 1, 4, 5, 6, 7. So in the T2G, how many unpaired electrons? Only 1 unpaired electron. Don't count all 3, only 1. The theory that can completely and properly explain the nature of bonding in carbonyls, okay, particularly carbonyl. Here we didn't talk about in CFT, in valence bond theory, Werner's theory, we didn't talk about the carbonyl, right? We talked about the carbonyl in case of weak field and strong field, but carbonyl is doing something different, that is back bonding, right? So back bonding, that is explained by molecular orbital theory. In which of the following complex the CFSE del octahedral value will be 0? You can count the other CFSEs over here. Let me do the first one. I have Fe, SCN6, right? So SCN is again a strong field ligand, 3 minus, so Fe 3 plus, Fe 3 plus 3d5, 1, 2, 3, SCN is in weak field ligand, sorry, CN is in strong field ligand, CN is, so 1, 2, which makes 0.4 into 3 in the T2G plus 0.6 into 2, that is in EG, so totally 12 minus 12, 0. So answer becomes option A. Just tell me other CFSE values as well. Then the correct order of following complex in terms of crystal field stabilization energies are. Again, same type of question. So I'm giving you the formula. You can just substitute it over there. CFSE, that is minus 0.4 into number of T2G electrons plus 0.6 into number of EG electrons. Include paired, unpaired, everything. Okay, number of electrons that you are placing it over there. Just let me know what is the answer in the comment. The correct increasing order of stability of the complex based on del octahedral value. Okay, stability. Let's see what are the values we are getting. Here that is in Mn3 plus. So the CFSE becomes how many electrons? In T2G Mn3 plus, that is in 3D4. This is a strong field ligand. So it will pair up. 3D4 means in T2G I will be having 4 electrons, plus in EG level I won't be having any electron. So which is minus 1.6 del octahedral. Next, cobalt 2 plus, which is the CFSE will become minus 0.4. Again a strong field ligand. Cobalt which will have 3D7. So T2G 6 electrons plus 0.6 into 1 electron in the EG level. So totally minus 2.4 plus 0.6, which is minus 1.8. Then Fe2 plus. Fe2 plus 3D6. So 3D6 strong field ligand. So which will become CFSE as minus 0.4 into 6, and EG I don't have any. So minus 6 into 4, 2.4. Then Fe3 plus. Fe3 plus I'll be having 3D5 strong field ligand. So only in T2G level I'll be having electron minus 0.4 into 5, that is minus 2.0. So these are the values I got as in CFSE. So which one will become more stable now? The stability of the complex is based on the del octahedral value. Greater the CFSE value, more stable the complex is. The more negative of the CFSE value, the more stable of the complex. So as you can see, I have this one as first. So 3, then comes 4, then 2, and then 1. So this is the order of stability. More the CFSE, it can be of minus, but more negative value, more stable that would be. Clear? These questions will give you free marks, absolutely free marks if you know the concept. The d orbital electronic configuration of the complex among which has an highest CFSE. Again, you can do it very clearly now, right? You can drop it. See how many times the same CFSE value paramagnetic questions were asked. It was asked many times, more than 10 times. Again, which one of the following complex will have del octahedral value is 0 and mu value, that is 5.96. 5.96 means many times I told you that this number before the decimal point, that number you can take it as an unpaired electrons. It is a shortcut. It's not a true fact, but that works. Okay, so this number that will be equal to your unpaired electrons. So 5 unpaired electron complex I have to find which is having del octahedral as 0. Okay, so Fe F6 4 minus Fe2 plus, right? So there is a possibility of unpaired electron because weak field ligand is present. So Fe2 plus, that is having 3D6 configuration, weak field ligand. So which is T2G 4 EG 2. So 4 into 0.4 16 and 2 into 6 12. So which is not 0. Then what about Mn 2 plus 3D5. See 5 unpaired electrons are there. So let's see. T2G 3 EG2. So which makes the option B as your right answer. Please check out C and D as well. Identify the homoleptic complexes that is are low spin. E's are low spin. More than one can be correct. The options are different. Okay. They are asking for homoleptic complex. Homoleptic means same ligands. So option A is definitely wrong. What about B? B is having fluorine as a ligand, works. C is also having D. Okay. So definitely not A. Then low spin complex. Low spin means number of unpaired electrons are less. Here I have cobalt 3 plus, where T2G cobalt 3 plus is 3D6. So weak field ligand 3D4 Eg2. And iron 2 plus 3D6 again, but strong field ligand. So T2G6 Eg0. T2G6 Eg0. Chromium, it's a weak field ligand. So Cr2 plus 3D5, 4s1 is the configuration of chromium. Now it will be 3D4. So T2G 3Eg1. This is having a 4 unpaired electron. This is having again 4 unpaired electrons. But these two, look at the structure, it is not having any unpaired electron, which makes it low spin. So C and D is the complex that is homoleptic and low spin. So many times they have asked about which of the following is homoleptic, that related questions. Okay, homoleptic means same ligands must be present over there, and heteroleptic means different ligands. Okay, the number of optical isomers exhibited by the ion complex obtained from the following reaction. So FeCl3 plus KOH with oxalic acid, which will form K3Fe oxalato ligand. Okay, what they are asking is number of optical isomers. So this is an A3 type, right? So which can exhibit optical isomerism of D and L isomer. So answer to this question is 2. Stereoisomers possible for the complexes. This one CrCl3 pyridine 3. So which is an A3B3 type clearly. Fat and Meridional isomers are possible. Correct. 2 isomers. And what about this one? A2AA2. Remember A2AA2, where I just draw it for you. ClCl and oxalato. This isn't, Cl is in the same side, so which makes it cis. This can exhibit optical isomerism as well, which is D and L, right? So if I'm drawing a trans isomer of the same thing, oxalato, ClCl, which is on the opposite side, this is trans. So including D and L of optical isomer, total 3, and this is 2. The number of complexes which show optical isomerism among the following is. Okay, so this is just now we saw cis, which can show optical isomer AA to A2 type, right? Remember that. Then I have this AA3 type and cis. This type, again, it can also show cis. This can also show. Trans will not show. Trans will not show. So total 4 complexes can show optical isomerism. The set which does not have ambidentate ligand is. So ambidentate ligand is something which has 2 donation side, but only one at a time it can donate. For example, I have Cn. So nitrogen can also donate electrons, carbon can also donate electrons. But either it can go with cyano or cyanide. Okay, Nc or Cn. Not both the electrons can donate at the same time. That is what ambidentate ligand. Other examples are nitro, thiocyanate. Okay. So here you see nitro is there, thiocyanate is there. Thiocyanate is there, nitro, and what about D? I don't have any ambidentate ligand. So which is a very simple question but asked many times about ambidentate ligand. Please be aware of it. Option D is your right answer. From the magnetic behavior, this is paramagnetic and this is diamagnetic. What is the shape? Okay, so they have mentioned this is paramagnetic, which means that is not undergoing any So nickel 2 plus complex 1, 2, 3, 4. Nickel 2 plus is 3D 8. 1, 2, 3, 4, 5, 6, 7, 8. Paramagnetics and also weak field ligand. Weak field strong field concept introduced in CFT only. This type of writing is VBT. So which is in starting from sp3, right? Hybridization is sp3. So that is tetrahedral. Okay. So this is tetrahedral. What about carbonyl? That is diamagnetic, they said. They are saying that is diamagnetic. Nickel 0 oxidation state. Always remember, whenever this carbonyl ligand comes, the oxidation state of the compound, central metal atom is 0. Okay. So 3D8, 4S2, which is again 3D8, 3, 4S2. It's completely filled. So definitely it is in strong field ligand. So these two electrons can shift over here to do the exchange, and remaining I'll be having s orbital starting, that is sp3 hybridization, which makes this one is also tetrahedral. Okay. Related question. COF6 3 minus copal 3 plus, that is weak field ligand. So starting it from S only. So sp3d2. Then nickel 2 plus Cl4 weak field ligand again. 3D8 configuration. So no para. Starting it from S, sp3. And cobalt 3 plus strong field ligand, which can undergo para, which will ended up with D2 sp3. And nickel Cn4, that is nickel 2 plus strong field ligand, so which can undergo para to form dsp2 configuration. The type of hybridization and the magnetic property of MnCl6 3 minus R. Very simple question, right? Cl6, which is Mn3 plus state, which makes it 3D4. 4 is 0. 1, 2, 3, 4. Or they are asking magnetic property. Cl is a weak field ligand, will not undergo para. Again, this is having 4 unpaired electrons. So options 4 unpaired, 4 unpaired. What about the paramagnetic hybridization? Becomes starting it from s orbital only, 4s. So sp3d2. Very simple question. You can answer it in seconds. The number of species from the following that are involved in sp3d2 configuration. Cobalt, which will have D6 configuration. So if that undergoes para, then there will be two empty spaces. So this will be D2 sp3. The hybridization of sulfur. Hybridization rule I told you, right? Take the valence electrons divided by 8 or 2, depend on the condition, and you will get the lone pair and bond pair electrons. You can match it with VSEPR. So S sub 6, that is sp3 d2, and CrF6, which will belongs to again D2 sp3, and Gopal 3 plus weak field ligand, that is sp3 d2. Gopal 3 plus, that is having empty s orbital. So that is a weak field ligand, but still that is having an empty orbital. It's starting from sp3 d2, and manganese 3 plus strong field ligand. Hybridization is d2 sp3, and this will become sp3 d2. So number of sp3 d2s are 3. Consider the following reaction. K2Cr2O7. With KOH it is forming A, and with A with sulfuric acid it forms B. This is from DNF law. The dichromate and permanganate. What is the hybridization? Why that is forming colors, and what are the important reactions do we have? That gives us more questions. So K2Cr2O7 in basic condition, what that will give. They also mentioned the removal of H2. So what we can expect? KCrO4, right? Will form again K2Cr2O7. First I have added base, again I have added acid. So remaining it will form K2Cr2O7. These two are the products. Acts as a strong oxidizing agent in acidic solution. During this process, what is the oxidation state change? So dichromate, which is in Cr2O7 2 minus, that is in +6 oxidation state. In acidic condition, that acts as an oxidizing agent. So which means itself reduces, it gains electron to form Cr3 plus. Okay, so that is the change, +6 to +3. Neutral or alkaline medium, MnO4 minus oxidizes thiosulfate 2. So thiosulfate, what is the formula? S2O3 2 minus. MnO4, it oxidizes thio by reducing itself to MnO2, right? So it changes thiosulfate to SO4 2 minus. Thiosulfate to sulfate. Lanthanide ions with 4F7 configuration. So these are some important lanthanides and actinides to remember on. Okay, so many questions asked with diasporium, europium, gadolinium, terbium, samarium, cerium. Okay, and lutetium also. So mostly the questions will be covered from these elements. If you are lucky enough, they will ask you from this question only. Now you know, right? So 4F7 configuration. Let's see. Europium, the general electronic configuration in atomic state, that is Xc 4F7 6s2. So after losing 2, that will be 4F7. So europium. And gadolinium. Gadolinium general electronic configuration is after xenon 4F7 5d1 6s2. After losing T electrons, it will become 4F7. So that is also. Then europium 3 plus won't be coming, that becomes 4F6. Then terbium. Terbium configuration is after xenon, that becomes 4F8 6s2. So 3 plus, that will be 4F7. So that can be counted on. Then samarium. Samarium after xenon 4F7 6s2. Sorry, 4F6 6s2. Losing 2 electrons, it becomes 4F6, so which can't be counted. So remaining A, B and D are your answer. The pair of lanthanides in which both elements have high third ionization energy. Okay, so again gadolinium, europium, lutetium, ytterbium. So let's see. Gadolinium, I already told you, after xenon 4F7 5d1 6s2. So third ionization energy. So which means I removed all these two. I want to remove 5d1. So that is easy, right? So it is not our answer. So A is not our answer, B is not our answer. What about lutetium? Lutetium, the configuration is after xenon 4F14 5d1 6s2. Again the same thing, correct? So which can't be our answer? What about europium? Europium I gave you, that is Hc 4F7 6s2. So it is tough to remove the seventh, half-filled configuration. So which makes europium answer is right. And ytterbium is also having 4F7 configuration over there. That makes option D as your right answer. The current order of atomic radii. As you can see, here they have given helium, nitrogen, europium and cerium. The atomic radii here follows the order europium, then cerium. These are the questions from Lanthanide contraction compared with nitrogen. Nitrogen becomes least because that is top. As moving down the group it decreases, right? Because of the number of shells increases. CrCl3 XNH3 can exist a complex of 0.1 molar aqueous solution of this complex shows a depression in freezing point of 0.558 degrees Celsius. Assuming 100% ionization of this complex, the coordination number of Cr is. Okay, coordination number of Cr is 6, and what they are asking, the complex will be. Great. So the clue point over here is we have to find the I factor, right? 1/2 factor. They have given the freezing point. So delta TF is equal to I KF M. So delta TF value, that is 0.558, that is the difference, isn't it? So I, that I don't know, KF, that is 0.86, M, that is 1.1 molar solution. So which will give you the value of 0.558 divided by 1.86 into 0.1, which is 3. So I value will become 3, which means outside the coordination sphere I can have two ions, right? The first one, which is sphere, 1 ion, and outside the sphere I can have 2. Second one is not having that, third one is also not having that, because in that case that will be only 2, in this case that will be 4 ions, in this case only 1. Okay, which makes clearly option A is your right answer. Very simple question, isn't it? This is the number of electrons in T2G orbitals of the most stable complex ion. These ones, the nature of oxide of vanadium of the type. So from here we have to find the X value. That X belongs to the vanadium oxide. What is that type of vanadium oxide is? Very interesting question, right? So most stable complex ion among this. First one, Fe NH3 6 times, so Fe3 plus. Strong field ligand, so T2G. First of all, Fe has 3D5, Fe3 plus has 3D5 configuration. So all 5 goes here, Eg0. And the second one, Fe3 plus again, but T2G3 Eg2. And here also Fe3 plus, but which will be same as the first one. Among this, which will have more stable means more CFSE. Let's calculate CFSE for these two structures. 3D minus 0.4 into 5 plus 0, that will be, because Eg is 0, that makes it 0.2. Here, minus 0.4 into 3 plus 0.6 into 2, which is 1.2 minus 1.2 plus 1.2, that's 0. So which makes this complex as a stable one, Eg5. I'm not referring to ion complex of this first one and third one. I'm just saying T2G5, that complex is stable. So that electron of T2G, that is fine. So the vanadium is V2O5. V2O5 is what type of oxide? Amphoteric oxide. Okay, so that's what they are asking. Choose the correct statement about hydrides of group 15 elements. On moving down the group, the bond strength. On moving down the group, the bond strength of metal to hydride, the bond strength decreases. Okay, so due to which what will happen? Bond strength is increases means that becomes stability will become less and less. So the first option which says NH3 is more than the bismuth right? So which is in right statement. And B, the reducing ability of the hydrides increases in the order. Then obviously the opposite would be the correct. So that is right. Among the hydrides, NH3 is a strong reducing agent while BH3 is a mild reducing agent. So which is not true, it's just ulta. The basicity of hydrides increases in the order. Basicity of hydrides generally decreases down the group and increases across the period. So which says option D, the statement D is also false. A and B are the only right statement. So basicity, that is decreases down the group. Hydride stability, that is also decreases down the group. Remember that. The following oxo acids of sulfur contains S in 2 different oxidation states. So the first one, H2S2O3, the structure will look like this: OH, OH, and double bond O, double bond S. So where here I'll have -2 oxidation state, this side I'll have +6 oxidation state. So which makes option A is your right answer. Then arrange the following species in the order of increasing ionic radii and explain the trend. So these are periodic properties related questions. If you're thorough with it, you can skip. If you're not thorough, just want to check, you can listen. So Al3 plus, Mg2 plus, Na plus, F minus, O2 minus, N3 minus. So many questions were asked based on this ionic radii. So all the species are isoelectronic. So we shall have 10 electrons in it, right? So for an isoelectronic species, particularly for isoelectronic species, isoelectronic means same number of electrons. The radius, ionic radius, is directly proportional to its nuclear charge. Okay, nuclear charge is nothing but you can take the atomic number, protons, number of protons. Okay, so if I'm taking Al3 plus, that is 13, Mg2 plus 12, Na 11, F 9, O 8, nitrogen 7. So what will be the order? Al3 plus less, then Mg2 plus, Na plus, F minus, O2 minus, N3 minus. Okay. Questions can be asked from isoelectronic species also and ionic radii, atomic radii also. Next, then arrange the following elements in order of increasing first ionization enthalpy. Lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. So, usually what is the trend? Ionization enthalpy increases on moving left to right and decreases down the group. Again, because of the effective nuclear charge, it's holding it up, so it needs more energy to remove, and decreases down the group, the shell number increases, so which can easily be removed from the valence shell. Here, important exception is there between our beryllium and boron. Lithium, that is 1s2, 2s1, beryllium 1s2, 2s2, boron 1s2, 2s2, 2p1. So usually what we said, it increases, right? But compare beryllium and boron, it's having, boron supposed to have more, no? But it is not, it's having less, because 2p, that is having only one electron in it, which is a partially filled. So it is very easy to remove the electrons, right? So beryllium is having more energy, it's require more energy than boron. Then carbon 1s2, 2s2, 2p2. Oxygen 2s2, 2p4. So this is nitrogen 2p3. Oxygen 2p4. Fluorine 2p5. So fluorine will have highest. It doesn't want the removal of electron. It wants the electron, right? Fluorine is having one of those highest. It's having highest ionization enthalpy. So the order goes like this: lithium, boron, then beryllium, carbon, oxygen, nitrogen and fluorine. Okay, again the same reason rise for nitrogen also. Nitrogen is having half-filled configuration, oxygen is partially filled. So removal of half-filled is very difficult because that is more stable. Removal of completely filled is further difficult. That's why these inert gases are having very high ionization energy. Arrange fluorine, chlorine, bromine, iodine in order of electron gain enthalpy, most negative to least negative. So comparing electron gain enthalpy. So energy required to add an electron, right? So in this case, fluorine is having less value than chlorine. Why is it so? Because fluorine is smaller in size, right? It is having more effective nuclear charge. If I want to add the electron, it's very compact. The incoming electron faces the severe electron-electron repulsion, right? Due to its smaller size. So which makes the order as chlorine comes first, then fluorine, then bromine, then iodine. The element has successive ionization energies, En1, En2, 3, 4, 5 given. Determine the number of valence electrons, group number, explain the large sum. So this is not MCQ, but I want to explain these exception cases present in periodic table. Okay, so as you can see, ionization energy means energy required to remove an electron. So En1 is 800, 2 is having more value than 1, then 3 is having furthermore, 4 is having furthermore, and 5 is a lot, right? So which means analyzing the values of electron potential, this value 3000 to 25,000, that is very, very huge, right? Which means there should be a very big stability over there to remove it. The first 3 electrons are valence electrons, so which we removed easily, but the 4th electron from noble gas configuration, so that's why that is so difficult. So number of valence electrons here, that is 3, so the group number is 13, right? And the large jump, it's because of the noble gas configuration cross. So what we can suggest is, that is aluminium neon configuration. After that I have 3s2 3p1. So removing these is easy, but neon, that makes it 25,000 something. The incorrect electronegativity order. Electronegativity means the tendency of the atom to attract the electron towards itself, right? So what are the correct statement or what are the incorrect order? So the first one, sulfur, then chlorine, oxygen and fluorine. Fluorine always will have more, that is a more electronegative atom. Always remember, left to right electronegativity increases, like we say in, remember, ionization enthalpy, electronegativity and electron gain enthalpy, all 3 are increases left to right and decreases moving down the group. All 3 are same. So first one, that is right. Second one, aluminium, silicon, carbon and nitrogen. That is also true. Magnesium comes first, then comes aluminium, then boron and nitrogen. So aluminium is not less than magnesium. So this is an incorrect order. What about magnesium? 12, beryllium 4, 5 and nitrogen 7. That is right. So option C is the wrong answer. Sorry, right answer, wrong order. Arrange these in increasing acidic strength. Okay. So acidic, basic and amphoteric oxides. Okay. So remember, Al2O3, that is amphoteric. And SiO2, that is weakly acidic. These metal oxides, no? Those are basic oxides basically, and these non-metals are acidic oxides. Remember it like that. Among this, these are Al2O3, that is amphoteric. And here I have P2O3, that is non-metal oxide, that is acidic. And SO2, that is more acidic, more towards non-metal, so more acidic. So what would be the order? Al2O3, SiO2, P2O3 and SO2. So basically acidic and oxides and basic oxides means when we are adding water, if that is giving you bases, that is basic oxide. If that is giving you acid, then that is acidic oxide. For example, with SiO2 I am adding NaOH. So that's forming sodium silicate and H2O. So that's in weakly acidic, so that can react with NaOH. Okay, so if I'm taking P2O3, P2O3 is acidic. How I can check it? I'm adding water. It's forming phosphorus acid. So that makes it acidic. E has an electronic configuration of this. Determine its atomic number, name of the element, identify its block, group and period, and what type of element this is. This can be asked as a complete separate question. I'm going to cover all together. Okay. So, first of all, observe the electronic configuration given. 5f14, 3, 6d1, 7s2. So, count the number of electrons over here. That will give you atomic number. So, for radon, that is 86, right? So 86 plus 14, 1 plus 2, which is 90, 100, 101, 103. That is atomic number. What is the IUPAC name? 103 means what is the name? Uni for 1, 0 nil, and 3 tri. In the end, we will say we'll add yum. So you need nil trium, that is the name. Identify its block. So block, the incoming electrons add where that is getting added in D. So that is D block. Then identify the group. It's group 3. All F block elements are belongs to group 3. So this is group 3. Then period. Period is the 7th period because 7 is 2 is there. What type of element is this? So 4F14 is 5F14 that is filled completely, which means that is a transition metal that to an inner transition metal. Okay, so using the electronic configuration, how much we can discover, how many questions can be asked. Just observe that. Okay, so keep practicing more and more questions. Hope it helps. If you want any particular question or any particular chapter to be discussed, let me know in the comments. Thank you.